Hello students, I am Sachitrakar. Welcome to Cars Physics. We are continuing moving charge and magnetism. In previous lectures we have discussed Biot-Savart's law and one of the application of Biot-Savart's law. In this lecture we will discuss another application of Biot-Savart's law, that is magnetic field due to a current carrying circular loop and due to current carrying arc, means a part of circle. Okay. So according to Biot-Savart's law, we have got expression of magnetic field due to an elemental length of conductor carrying current. Okay, means a very small length of conductor carries current. Okay, suppose this is a conductor of any shape. Okay, any shaped conductor, and this conductor carries current I. This conductor carries current I. Let's consider an elemental length, a very small length, that this part of conductor is a dl. So if you take very small length of a conductor of any shape, this is a curved shape, then a small part of a curved conductor is a straight line, is a straight part of conductor. Okay, this small part of conductor is dl, and as we have discussed, direction of elemental length dl, direction of dl is taken along the direction of flow of current. So this is direction of dl along the flow of current, and this is any point P. Okay, and position vector for point P is r, and this angle is theta. Theta is angle between dl and r. Okay, then according to Biot-Savart's law, magnetic field due to this elemental length of conductor dl carrying current I at point P is given as, magnetic field at point P is given as dB is equal to mu naught by 4 pi I dl sin theta divided by square of distance, means square of magnitude of position vector, and in vector form we have discussed dB is equal to mu naught by 4 pi I by r cube into dl cross r. Okay. So direction of magnetic field can be simply taken. Simply we can decide or determine direction of magnetic field due to this elemental part of conductor along the direction of dl cross r. And there are several rules. Of course we have discussed how to decide direction of magnetic field. Okay, here this is direction of dl, this is direction of r, so dl cross r is inwards. So in this case magnetic field is inwards. Okay, cross field. Again we have discussed, if the point P either lies, if the point P lies along the direction of flow of current, means if theta is 0 degree or 180 degree. If theta is 0, point P lies along the direction of current, and if theta is 180, again point P lies along the direction of current. In both cases magnetic field is 0. Magnitude of magnetic field is 0. Okay. So all these we have discussed in previous lecture. Then in this lecture we are going to discuss magnetic field due to circular loop and arc. Current carrying due to circular loop and arc carrying current. Carrying current. Okay. So we will go through the derivation, first derivation, then we will go through some numericals on the basis of this theory, and of course we may use the formula of previous theory, means magnetic field due to straight current carrying conductor. We will discuss all gradually. First derivation. Magnetic field due to a circular loop. First let's consider a circular loop carrying current. Then we will go to magnetic field due to arc. Okay. So let's consider this is a circular loop, okay, which carries current I. I have taken current in anticlockwise order, and the radius of the circle is R. Then we have to get what is magnetic field at the center of circular loop. Magnetic field at the center of circular loop carrying current. Magnetic field at the center of circular loop carrying current. Let's consider a circular loop carrying current I, and radius of the circle is R. Okay. So magnetic field dV, as we have discussed, according to White-Savart's law, for an elemental length of conductor dl, position vector is R. At point P, if this angle is theta, then magnitude of magnetic field is given as mu0 by 4 pi I dl sin theta divided by r square. This is basic formula. Again we can determine direction by right hand thumb rule here inwards. Okay. So this whole circular loop may be considered to contain a number of elemental lengths each of dl. Let's consider this is an elemental length dl. This is an elemental length dl. If length is very small, this is dl, and direction of dl is taken along the direction of current. Current is not a vector, but current flowing in anticlockwise order in a curved path. Then at any point, direction can be determined by drawing a tangent. So at this point, direction of current is along the tangent, and this is direction of dl. Okay, direction of dl is taken along the direction of current, and we have to find magnetic field at the center of the circle, and here this is position vector R. Now angle between them is theta. Theta is 90 degree. Then magnetic field dV due to this elemental part of conductor dV is mu0 by 4 pi I dl sin 90. Theta is 90 degree. Sin 90 is 1 divided by square of distance. If you want to get direction, then in vector form dV is equal to mu0 by 4 pi r cube I into dl vector cross r vector. So here, this is direction of dl, this is direction of r, so dl cross r is outward. dl cross r is outward, means dot field. Similarly, you may take a number of elemental parts dl, just take here dl, this is dl. So direction of dl is along the direction of flow of current, and direction of current at this point can be determined by drawing a tangent. This is direction of current, so this is direction of dl. Again, join to the center, then this is r. An angle between dl and r is again 90 degree, and again magnetic field is same, and direction is dl cross r, again outward. So you may consider here dl, and direction of dl is along the direction of current, along the tangent, and this is direction of r, and this angle is again 90. This angle is again 90, again dl cross r, this is r. dl cross r is in what? dl This is R, dl cross R is, sorry, dl, this is R, dl cross R is outward. And you may take here length dl, elemental length and direction of current. This is direction of dl, this is direction of dl, and this is radius. This angle is again 90 degree. So dl cross R again outward. So you may take here also dl. This length is dl, and this is R. This angle is 90 degree. This is dl. Again, dl cross R is outward. So in each case, we have observed if the whole circular loop is divided into a number of elemental parts, each of length dl, then magnetic field due to each part, due to each elemental length dl, is mu 0 by 4 pi I dl by r square. Sin 90 is 1 and direction is outward. Okay. Then what is total magnetic field due to whole circular loop? This is magnitude. Let's take magnitude, direction is outward. To get total magnetic field due to the circular loop, let's integrate both sides. Integration of the mu naught by 4 pi I by r square constant, then integration of dl. So elemental length is dl, then we have to get magnetic field due to total length of the circular track, circular loop. Then total length varies from 0 to 2 pi r. Then integration of dv is d, mu naught by 4 pi I by r square. Then integration of dl is L, 0 to 2 pi r. Then b is equal to mu naught I by 4 pi r square into 2 pi r minus 0. Then magnitude of magnetic field is mu naught I pi get cancelled, r square, 2, 4, then it is 2r and direction is outward. Mu naught I by 2r. So I am writing here for total circle carrying current I of radius r, magnetic field at center B is equal to mu naught I by 2r. Of course, you may take in general the formula is mu naught Ni by 2r, where N is number of turns. Here number of turn is 1, so we may take mu 0 Ni by 2r. Here number of turn is 1, so magnetic field is mu naught I by 2r. This is formula for magnetic field at the center of a circle carrying current I. Okay. Then let's find different cases. Can I erase it now? Okay. Suppose it is given to get magnetic field due to a semicircular loop. Semicircular current carrying conductor. This is a semicircle. Current flowing, you may take clockwise or anti-clockwise, current is I. This is center, so radius is R. So what is magnetic field at the center of the semicircle carrying current I? Semicircular wire carrying current I, what is magnetic field at the center? In similar way, we may write, according to Biot-Savart's law, this is formula for magnitude of magnetic field, dB is equal to mu naught by 4 pi I dl. See, if you take dl, suppose I am taking here dl, straight path dl, along the direction of current, this is dl and this is r. This is r. So again here, theta is 90 degree, I dl sin 90 divided by r square. So sin 90 is 1, then dB is equal to mu naught I by 4 pi r square into dl. Is it clear? Then to get total magnetic field, let's integrate both sides. dV is equal to mu naught I by 4 pi r square integration of dl, and length varies from 0 to total length of semicircle is 0 to pi r. Then V is equal to mu naught I by 4 pi r square integration of dl is L, length varies from 0 to pi r. So B is equal to mu naught I divided by 4 pi r into pi r minus 0, pi get cancelled, r square, r cancel square. Then magnetic field B is equal to at the center of semicircle. At the center of semicircle carrying current I, then B is equal to mu naught I divided by 4r. Again direction is outward. Anticlockwise outward, or dl cross r is outward. So what is to be observed? For a total circular loop, magnetic field is mu naught I by 2r, and here for semicircular loop, means half the circle, magnetic field is mu naught I by 4r. So magnetic field due to semicircle is equal to half magnetic field due to a circular coil. See, magnetic field due to complete circle is mu 0 by 2r. So mu 0 by 2r into 1 by 2 is equal to mu 0 by 4r. So this is magnetic field. This is magnetic field due to semicircle. Okay, semicircle. So magnetic field due to semicircle is equal to 1 by 2 into mu naught I by 2r. But mu naught I by 2r is magnetic field due to circle. So we may write this is equals to half into magnetic field due to circle. This is the concept. Just remember this. It is easier to remember. For total circle, magnetic field is B. Then for semicircle, magnetic field is B by 2, means half the magnetic field due to total circle. Okay. Then similarly, suppose I do consider a quarter circular conductor, quarter circular wire carrying current I. Okay. So this is a quarter circular conductor. See, this is semicircle, or you may take circle. This is a circle, complete circle. Okay. Suppose it carries current I. Quarter circle means 1/4 of the circle. Let's consider this part, only this one, quarter circle, and its radius is again r. So if you take dl here, then direction of dl along the direction of current, and this is r. This is center, direction of r, and this angle is 90 degree. So again, dV is equal to mu naught by 4 pi I dl sin 90 divided by r square, and dV is equal to mu naught by 4 pi r square into I divided, mu naught I by 4 pi r square into dl. Now integrate both sides, integration of dV, mu naught I by 4 pi r square integration of dl. Here length varies from 0 to pi r by 2. Quarter circle, semicircle, length of semicircle is pi r, length of quarter circle is pi r by 2. Just put here, and integration of dv is b. mu 0 I by 4 pi. Directly I am putting this value in the integration of dl is L. In place of L we can take pi r by 2 pi r get cancelled, and magnetic field is equal to mu naught I divided, this is r square, this is r square is cancelled, then it is 4 into 2 8 r. This is magnetic field due to a quarter circle, means magnetic field due to quarter circle is mu naught I by 4r. Magnetic field due to complete circular coil is mu 0 I by 4r. So this is 1/4 of circular part. We may write 1/4 into mu 0 I by 2r. So this is equals to 1/4 of magnetic field due to circle. This is the concept. If you are taking semicircular track, then you take half the part of circle. You take half the part of magnetic field due to a circle. If you are taking a semicircle, then take 1/4 part of magnetic field of circle. This is the trick. Okay. So suppose any angle is given. See here, angle is 90 degree, pi by 2. Okay. And for semicircle, angle is pi. For total circle, angle is 2 pi. For any value. Okay. You may take an arc subtending an angle theta about the center. Okay. Let's consider this is an arc. We don't know what's its length. Let's its length is L. We don't know. Then this is part of a circle. This is part of a circle. Half part of circle, semicircle. 1/4 part of circle, quarter circle. This is any part. We don't know how much this is. So suppose this much length is considered. Okay. This is center of the circle. This much length is subtending an angle about the center is let theta. So what is magnetic field due to this arc carrying current I? Okay. Total length is L. So if we do take current is I, at any point we may consider this is elemental length dl along the direction of current. This is direction of dl joined to center. This is R. An angle between dl and R is again 90 degree. Then magnetic field dv according to White-Savard's law, mu naught by 4 pi I dl sin 90 divided by r square. Here theta is 90. Here theta is 90. So dv is equal to mu naught I by 4 pi r square into dl. Then simpler. To get total magnetic field, let's integrate both sides. Okay. Then integration of dv is equal to mu naught I by 4 pi r square into integration of dl. Length varies from 0 to L. Okay. Then dv, integration of dv is b. Mu naught I by 4 pi r square. Integration of dl is L and limit varies from 0 to L. So this is L minus 0, and finally magnetic field is mu naught I L. This is L minus 0. So L, or you may take mu naught I by 4 pi r square into L minus 0. Upper limit and lower limit, and you get magnetic field is mu naught I L divided by 4 pi r square. But this arc length L subtends an angle theta above the center. So theta is given. How can you calculate magnetic field? If length is given, then it's okay. If length of arc is given, then it's okay. Then how to find the magnetic field if theta is given? In general, theta is equal to arc length divided by radius. You know it. Theta is equal to arc length divided by radius. We do consider for small angle, and here theta is any value of angle, and theta is equal to arc length is L, radius is R, then L is equal to theta into R. Then put here. Then finally, magnetic field for this arc is mu naught I by 4 pi R square into length. In place of length, let's put theta R. Then R square. Then magnetic field is mu naught theta I divided by 4 pi R. Direction, you may simply dl cross R outwards. Direction is outward. This is general formula for any value of theta. For an arc, the arc subtends an angle theta about the center of the circle, then magnetic field is mu naught theta I by 4 pi R. Okay. Then let's go to some numericals. I have some collection of numericals with me. So to match the answer, we may use. Okay. I think you have understood all the points. In general, for an arc which subtends an angle theta above the center, length of arc carrying current I, then magnetic field is mu naught theta I by 4 pi R. See, for a circle, you can match the answer for a circle. For a circle, theta is equal to 2 pi. Put here 2 pi, you will get expression for magnetic field at the center of the circle carrying current. For semicircle, theta is pi. Similarly, for quarter circle, theta is pi by 2, and so on. But remember, for this formula, theta is taken in radian, not in degree. Very important. Theta is taken in radian, not in degree. Convert angle, if given in degree to radian, then put here value of theta, you can get your answer. Okay, pi by 2, pi by 4, pi by 6, whatever be the value. Okay, is it correct? Fine. Then previous studies, in just previous lecture we have discussed magnetic field due to straight conductor. We have discussed several cases also. If the conductor, straight conductor, carries current I, then magnetic field at a distance R means at a point P. We can calculate if this angle is alpha 1, this angle is alpha 2. Then magnetic field at point P is given as mu naught I by 4 pi R into sin alpha 1 plus sin alpha 2. Just recall. This is conductor of finite length. Conductor, straight conductor of finite length. So, if conductor of infinite length, for infinite length, alpha 1 is equal to alpha 2 is equal to pi by 2, and magnetic field is mu naught I by 2 pi R, we have discussed. Then, for a conductor, infinite length in one direction. Infinite length in one direction. See, this is infinite length. This is a conductor of infinite length in one direction. In upward direction, it is infinite. So this end is finite, this end is infinite. Then magnetic field at a distance r. From one end of the conductor, magnetic field at a distance r means at point P. Here magnetic field is given as mu naught I by 4 pi r. And this is direction of current. Accordingly, magnetic field dl cross r, dl is taken along the direction of current, then direction is inverse. So we have considered, we have discussed different cases, but these are some outputs to apply in numericals now itself. Okay. Then some fundamental numericals. We'll approach one after one, and you will feel it very, very easier from very beginning. Before starting the numericals, I may commit you, though these numericals you will feel very, very easier. Okay. Question number one. Question number one. Okay. See, this is a circular conductor. This is a straight conductor. This is a straight conductor. Okay. Current flowing is R. So when current reaches here, it is divided into two parts. Again, finally, current leaves the circular coil R. So if radius of the circle is R, then we have to find magnetic field. Magnetic field at center O. We have to find magnetic field at center O. This is very easy. See, this is a semicircle, this is a semicircle. Okay. So as you know, resistance of conductor is rho L by A. Here we may consider this whole circular loop made up of same material, means resistivity is same, uniform wear. This may be considered as uniform wear. So A is constant, so resistance directly proportional to length. So this is a semicircular part, length is pi r. This is also semicircular part, length is pi r. So resistance of these two parts is same. So this current is equally divided. This is I by 2 and this is I by 2. So let magnetic field due to this part of this half of circle, means this semicircle is B1, and due to this semicircle magnetic field is B2. Then what is B1? B1 due to, or you may name it A, C, D, E. Magnetic field due to ACD. ACD. This is semicircle. So as we know, magnetic field due to semicircle is half the magnetic field due to circular coil carrying current, means mu 0 I by 4r. Mu 0 I by 4r, and at center, direction of magnetic field, simply turn your finger along the direction of flow of current, and at point O, turn your finger inside the circle. O is inside the circle, then magnetic field is inwards, or you may take dl cross r. Simple. Then magnetic field is inward, means cross. Then magnetic field due to AED, means due to this part. Again, this is a semicircular part. Magnetic field is mu naught I by 4r, and direction inside, O is inside. Curl your finger along the direction of current, and erect thumb represents direction. Erect thumb is outward, so direction is outward. See, these are two magnetic fields equal in magnitude but opposite in direction. So resultant magnetic field is 0, because magnitude is same and directions are opposite. So magnetic field is vector. So the resulting vector, the resulting magnetic field is 0. 2 is 0. Okay. Then question number 2. circular coil. Just imagine this is a straight conductor. We may think this circular coil is very close to the straight conductor, very close to straight conductor. Okay. The straight conductor carries current I, and the circular conductor also carries current I. Okay. Radius of the circle is R, center is O, then magnetic field at center means at O. Then see, from straight conductor this is infinite, this is also infinite, this is infinite long straight conductor, and the perpendicular distance is also R. Then magnetic field due to straight conductor, let due to straight conductor is B1, due to circular conductor is B2. Magnetic field at point O, due to the infinite length of conductor carrying current I is B1, and due to circular conductor is B2. Then what is B1? B1 due to infinite long conductor mu naught I by 2 pi r, and what is direction C? O is above the straight conductor, current is flowing along this direction, then turn your finger towards center, okay, simple turn, then it is outward. So it is that field, and magnetic field due to circle is B2, due to circle is mu naught I by 2r, and direction see, current is flowing in clockwise order, O is at the center, turn your finger in clockwise order, and erect thumb is inward. Means this is cross field. So if you compare between V1 and V2, here B2, magnitude of B2 is greater than V1. This is 2 pi r, this is 2r. So obviously B2 is greater than B1. Again, directions are opposite. So if two vectors are opposite in direction, then resultant magnetic field, magnitude of resultant magnetic field is B. It is equals to B2 minus B1. B2 is mu naught I by 2r minus B1 is mu naught I by 2 pi. Then the solve it, mu naught I by 2r into 1 minus 1 by pi. Then what is direction? Direction will be along B2, since B2 is greater than B1. Direction of B2 is inwards, so resulting field is inwards. Is it clear? Is it clear to all? Okay. Then question number 3. Then question number 3 is 0. Question number 3. 2 is here. This is a semicircular coil. This is a straight conductor. This is a straight conductor. Okay. This is up to infinite. This is also up to infinite. Current flowing is I. The same current is flowing through semicircle. This is also I. We have to find magnetic field at center of semicircle, and radius is R. So let magnetic field due to this straight conductor is B1. Magnetic field due to this semicircular part is B2. Magnetic field due to this semicircle is B3. We have to find magnetic field at O. Magnetic field at O. So B1 due to this straight conductor of infinite length in one direction, but point O lies along the direction of flow of current. So as we have discussed, if the point of observation lies along the direction of flow of current, then magnetic field is 0. Mu naught I by 4 pi r. mu naught by 4 pi into ideal sin theta by r square. Here theta is 0 degree. Along the direction of flow of current, theta is 0 degree. So magnetic field B1 is 0. Similarly, magnetic field B3 is also 0. Point O also lies along the direction of flow of current. So B3 is also 0. Then only magnetic field to be calculated due to this semicircular part, and magnetic field due to semicircular part is mu naught I by 4r. We have discussed that magnetic field due to semicircle carrying current I at the center is half the magnetic field due to total circle. The total circle mu naught I by 2r, and here half means mu naught I by 4r. Then direction, current is flowing in clockwise. So inward. Clockwise, just turn your finger, magnetic field is inwards. So cross. Very easy. Then question number 4. That question number 4. This is a semicircle. This is a straight part. This is a semicircle. We have to find magnetic field at O, means common center of two semicircles. Let current flowing is I, current is I, current is I, current is I. So radius of smaller semicircle is R1, semicircle radius of larger semicircle is R. See, magnetic field due to this straight conductor may be taken as B1. Magnetic field due to the semicircle of radius R1 is B2. Magnetic field due to this larger semicircle of radius R2 is B3. And magnetic field due to this straight conductor is B4. And as it is observed, point O lies along the direction of flow of current of this part and this part. See, I am naming. You will feel easier. P, Q, R, S, P, T. So magnetic field due to PQ is 0. See, along the direction of PQ, point O lies. So if point lies along the direction of flow of current, magnetic field is 0. Similarly, magnetic field due to RS, current is flowing along RS. Again, the point O is along the direction of flow of current. So magnetic field due to this part RS is 0. Then magnetic field due to Q, T, R. Q, T, R means smaller semicircle. This is smaller semicircle. Magnetic field is mu naught I by 4r. Then what is direction? Current is in clockwise order. We have to get direction of magnetic field at O. Just turn your finger, curl your fingers and erect thumb is inwards. Just apply right hand thumb rule. Curling finger along the direction of flow of current inwards means towards inward direction, and curling finger is rotated along the direction of current and thumb is inwards. So magnetic field is inward cross. Similarly, magnetic field due to O, this is not P, we take some other name. Suppose this is X, SXP. SXP. This is the larger semicircle, radius R2, this is R1. Then again, for semicircle, magnetic field is mu naught I by 4r, radius is R2. Then magnetic field at center, due to this semicircle, curl your finger, current is in anticlockwise order. If finger is curled along anticlockwise order, then magnetic field at O is outward. Anticlockwise, outward. Outward means a dot field. See, since R1 less than R2, so magnetic field due to QTR is greater than magnetic field due to SXP. Then resulting magnetic field is difference between these two, this is greater, this is smaller, so mu naught I by 4R1 minus mu naught I by 4R2, and magnetic field is mu naught I by 4 into 1 by R1 minus 1 by R2, and direction will be along the direction of greater one, QTR, means resulting magnetic field is cross. Is it clear? Again you feel easier? Okay, fine. Next question. These are very common questions. Then question number 5. Question number 5. This is a semicircle. These are common range questions. You can get these questions in any book. This is a semicircle. This is center of the semicircle. Center of the semicircle. O. And this is also a semicircle. Okay. And this is a straight part of conductor, and this is straight part of conductor. Radius of smaller semicircle is R1. Radius of larger semicircle is R2. And current flowing is I. Current is I. Current is I. And current is I. It can be simply observed that magnetic field due to this straight conductor at O is 0. Magnetic field due to this straight conductor at O is 0 because O lies along the direction of these two currents. This part, due to this part magnetic field is 0, this due to this part magnetic field is 0 because the point O lies along the direction of flow of current. So, magnetic field due to these two semicircles, let due to this semicircle is B1, due to larger semicircle is B2, then B1 is magnetic field due to smaller semicircle. Due to semicircle, magnetic field is mu naught I by 4R, and current in anticlockwise order. Just turn your finger about O. Inside the semicircle is O. Just turn your finger or curl your finger along the direction of or order of current, then erect thumb is outward. Outward. So this is dot field. Similarly, magnetic field B2 due to larger semicircle. This is R1, mu naught I by 4R2, and current is flowing again in anticlockwise order. Thus curl your finger. You want to get direction at O, magnetic field at O, curl your finger. Again it is outward. Again it is outward. Then dot field. So both the magnetic field due to these two semicircular parts are in same direction, dot field. So resulting magnetic field B is equal to V1 plus V2. So mu naught I by 4, mu naught I by 4, mu naught I by 4. Bring it common, then 1 by R1 plus 1 by R2, and direction is outward. Direction is outward. The previous question, direction. Due to difference between magnetic fields is inwards, and here two magnetic fields are added, so direction is same, means outward. Okay. Next. Right. The next question, a good question also. Next question is good question C. This is a semicircle. This is a semicircle. This is center of the semicircle O, and this is radius of the semicircle R. This is a straight conductor. Infinite length in one direction, and this is also a straight conductor, infinite length in one direction. Suppose we have to find magnetic field at O. We have to find magnetic field at O. So I am naming the conductor. This part of semiconductor is let 1. First semiconductor, this is 1, this is 2, and this is 3. So, for straight conductor of infinite length in one direction, we have to find magnetic field at O. Let current is I. Same current is flowing in the semicircle. Here also current is I. So magnetic field due to a straight conductor of infinite length in one direction. Magnetic field due to straight conductor of infinite length in one direction at O. See, here perpendicular distance is R, means theta is 90 degree. Then B1 is equal to mu naught I by 4 pi R. So magnetic field due to a straight conductor carrying current infinite length in one direction, just we have discussed in this lecture also from the beginning. Then direction, R2, current is flowing along this direction and we have to get magnetic field at O. Just curl your fingers towards O. Keep your fingers along the direction of current and curl towards O. Direction is outward. Direction is outward. Then magnetic field B2 means due to this semicircle. Due to this semicircle, we know magnetic field due to semicircle is mu naught R by 4R. Then direction of magnetic field at O. Then see, current is flowing in this order, means anticlockwise order. Then curl your finger to get magnetic field at O. Curl your finger along the direction of current and again direction is outward. Means again it is a that field. Then magnetic field this is B3 due to semicircle B3 and magnetic field B2 due to the straight conductor, again formula is same. Straight conductor of infinite length in one direction, mu naught I by 4 pi R. Then what is direction of magnetic field at O? Keep your fingers along the direction of current and curl towards O. Then again direction is outward. So all these magnetic field due to this straight conductor infinite length in one direction, this semicircle, and this is straight conductor of infinite length in one direction. All these magnetic fields of same direction means outward. So resulting magnetic field is equal to B1 plus B2 plus B3. Then B1 mu naught I by 4 pi R, B2 mu naught I by 4 pi R plus B3 mu naught I by 4 R. Solve it. B is equal to mu naught I by 4 R. This is common factor. 4 R. Then it is 4 R. 1 by pi plus 1 by pi plus 1. Then the resulting magnetic field is mu naught I by 4 R into 2 by pi plus 1 and direction is outward. Easier? Easier? Okay. The next question. Another beautiful question and a good question also. See. I will take a part of circle, not total circle. This is center of the circle. I am taking this part of circle. This is straight conductor of infinite length in one direction. This is also straight conductor infinite length in one direction. Current is I. Same current is flowing. Same current is flowing and radius of the circle is R. Then what is magnetic field at center? Again I am dividing. The straight conductor of infinite length is conductor 1. This curved part is conductor 2. Again the straight conductor of infinite length in one direction is conductor 3. Carrying all these conductors carrying current, then V1 is equal to 0. See, we have to find magnetic field at center and magnetic field at center O and O lies along the direction of this straight conductor of infinite length in one direction. If point lies along the direction of flow of current, then magnetic field is zero in accordance with Biot-Savart's law. Okay. Then magnetic field B2 due to this curved part. See what is the total angle in radian? This angle is theta 3 pi by 2. See, semicircle and quarter circle up to this pi by 2, and this is sorry up to this is pi, and this is pi by 2, 3 pi by 2. Then for any part of a circle, for arc, you know magnetic field due to arc mu naught theta I by 4 pi. Then here mu naught theta is 3 pi by 2. Current is I divided by 4 pi r. Pi get cancelled, and this is mu naught 3 mu naught I divided by 2 into 4 8 eta. And what is direction? Auto, magnetic field auto. Curl your fingers along the direction of current, and direction is outward, means dot field. Then magnetic field due to third conductor B3. This is also straight conductor of infinite length. This distance is also r. Okay. Then magnetic field is mu naught I by 4 pi r. And what is direction? Keep your fingers along the direction of current and curl towards O. Curl towards O. Again it is outward. So both are in same direction, and this magnetic field 0. Total magnetic field is B1 plus B2 plus B3. These are in same direction. So we add 0 plus B2. 3 mu naught I by eta plus mu naught I by 4 pi r. Now solve it. B is equal to mu naught I by r, mu naught I by r. Okay. Mu naught I by r, mu naught I by r, mu naught I by r. Then what you get inside the bracket? 3 by 8 plus 1 by 4 pi. 1 by 4 pi, and you may show direction is outward. Because B2 and B3 are in outward direction, so resulting magnetic field also in outward direction. Again it is easier. Okay. In some other question, we will raise the level of question gradually. I think this was question number 7. Question number 7. Then question number 8. This is also a good question. Again, this is a semicircle. This is a semicircle. This is center of semicircle O. Radius is R. This is a straight conductor of infinite length in one direction. Current is I. Same current is flowing I. Okay. And this is also a straight conductor of infinite length in one direction. Same current is flowing through all the parts, and we have to get magnetic field at O. Let's take this is conductor 1, semicircular part conductor 2, and again straight conductor into infinite length in one direction is 3. Then magnetic field due to first means this conductor is 0 because point O lies along the direction of current, so B1 is 0 as we have discussed. Then B due to semicircular part, at center of semicircular part, mu naught I by 4. Then what is direction at O? See, current flowing in anticlockwise order, curl your finger in anticlockwise order towards O, and direction is outward. Direction is outward. Then magnetic field due to third conductor B3. This is a straight conductor of infinite length. We have to get magnetic field at O. Again, this is distance R. then mu naught I by 4 pi r. And direction, keep your fingers along the direction of current and curl towards so, and direct thumb is again outward, means dot. Then resulting magnetic field is B1 plus B2 plus B3. So resulting magnetic field is 0 plus mu naught I by 4r plus mu naught I by 4 pi r. Then resulting magnetic field mu naught I by r into 1 by 4 plus 1 by 4 pi. You can add it and resulting direction is dot. Both are dot. Okay. 4 you may bring 4 common also. 1, 4, 4. Okay, this is easier than next question. Next question, I think it is a good question. Okay, very good. Good question. Question number 9. Question number 9. Okay. This is a circle of radius r. Circle of radius r. This part is removed. This part is removed. This is a circle of radius r. This is an arc. This distance is 2r, and obviously this is r. So radius of this arc is 3r. This is only 2r. Then total radius is 3r. Then current is flowing I. Same current is flowing I. Same current is flowing I. Then we have to get magnetic field at common center O. This is an arc. This is an arc. We have to find magnetic field at O. So again, I am taking, this is conductor 1, straight conductor. This is conductor 2, straight conductor. This curved part is conductor 3. This curved part is conductor 4. Then obviously magnetic field due to first conductor. Conductor 1 is 0 because point O lies along the direction of current, and similarly magnetic field due to second means number 2 conductor is 0. Current is flowing along this direction and point O lies along the direction of flow of current, then V1 and V2 are 0 due to these straight conductors. Then magnetic field B3 due to this curved part, and you know, as we have discussed previously, this total angle is 3 pi by 2, means theta is 3 pi by 2, mu naught theta, theta is 3 pi by 2, mu naught theta I divided by 4 pi r. Then B3 is equal to pi get cancelled, 3 mu naught I divided by 2 into 4, 8 r. Then what is direction? Current is flowing in clockwise order, about O, we have to get magnetic field. Then curl your finger along the direction order of flow of current towards O, then direction is inwards. Curl like this, inward. Then magnetic field due to fourth conductor, this angle is pi by 2. Very clear. Then B4 is equal to mu naught theta, theta is pi by 2, theta I by 4 pi r. Then B4 is equal to pi get cancelled, mu naught I by 8 r. Then what is direction? Current is flowing in this order, we have to get magnetic field at O. Curl your finger towards O and direction is inwards. curl your finger towards O and direction is inwards. Then same direction. So B3 and B4 are in same direction, B1 and B2 is 0. Then total magnetic field B is equal to B1 plus B2 plus B3 plus B4. These two are 0, 0. B3 and B4 are in same direction, so we can add 3 mu naught I by 8R plus B4 mu naught I by 3 by 8. This is 1 by 8. Okay. Just check it once. Just check it once. I think answer is given 5 by 12 mu naught by R. Check it once. Mu naught theta 3 pi by 2 into I divided by 4 pi R. 3 mu naught I divided by 2 into 4 8 R. Okay. Then B4. Oh, here the mistake. Here radius is 3R. Here the mistake. Radius is 3R. Then 4 into 2, 8. 8 into 3, 24R. Okay. Then this is 24R. Mu naught I by 24R. Then B is equal to mu naught I by R. Mu naught I by R. Mu naught I by R. Then inside bracket 3 by 8 plus 1 by 24. Then this is equals to mu naught I by R. LCM is 24. 3 into 3. 9 plus 1. So B is equal to mu naught I by R into 10 by 20. Means 5 by 12. 5 by 12 into mu naught I by R, and direction is obviously inwards. Yes, answer is mu naught by R into 5 by 12. Okay, this was the mistake. Then last question. Again a good question, I think. Okay. Question number 10. Question number 10. See, this type of question you may face in future. This is x-axis. This is y-axis. Okay, and obviously this is z-axis. This is z-axis. Okay. Suppose this is a semi-circular coil. This is a semi-circular coil, and this is a straight part parallel to z-axis. This is a straight part parallel to z-axis. Okay. Let current flowing. This is infinite long in one direction. This is infinite long in one direction. This is z-axis. Okay. And current is flowing this is z-axis. The direction of z-axis. Okay. Current is flowing I. Same current is flowing I. Same current is flowing I. These two are straight conductors along z-axis. Along z-axis. Along z-axis. And this semicircular loop lies on XY plane. Then we have to get magnetic field at O. We have to get magnetic field at O. Okay. Then numbering. Let this is number 1, the straight conductor of infinite length. This is number 2, straight conductor of infinite length. Okay. and this is conductor 3, means semicircular part. Okay. Then for straight conductor 1, B1 is equal to the straight conductor of infinite length in one direction, as we know, mu naught I by 4 pi r. Mu naught I by 4 pi r, but you see what is the direction of B1. See, current is flowing along z axis, and this is r. This is also r. Radius of semicircle, just think. This is xz plane. This is x axis, this is z axis, this is xz plane. Okay, and current is flowing along z axis. Then what will be direction? How can you determine direction? Okay, just imagine you have taken a elemental length dl here along z axis. Okay, and O is at the origin. We have to get at O. Then this is the direction of current. I am showing like this. This is the direction of current. Curl towards O. Then this is the direction of magnetic field. See, along z axis, this conductor 1. Along z axis, current is flowing along z axis. So keep your fingers along z axis and turn towards O. Then direction is downward. Downward means opposite to positive y-axis. This is y-axis. Okay, along this direction, fingers and turn towards O. Then if fingers are curves, then erect thumb represents direction of magnetic field. Downward means opposite to y-axis, so direction is minus j. Okay, and similarly B2, again it is along z axis, but direction of current is opposite, of course. Then this is direction of current along z axis, and we have to get magnetic field at O. Keep your fingers along the flow of current and turn towards O. Again direction is opposite to y-axis. Then this value is also mu 0 I by 4 pi r, and direction is minus j cap. Okay. Along this direction, current turn towards O, and direction is downward. Downward means opposite to positive y-axis. Opposite to positive y-axis means along negative y-axis. So unit vector is minus j cap. Then for semicircular part, magnetic field is V3. You know its magnitude, mu 0 I by 4 r. Then what is direction? About the center, curl your finger along the direction of current towards O. Direction is inwards. See, outward direction is z axis, inward direction is outward direction is z axis. So inward direction is along negative z axis, means direction is minus k. Is it clear? Then resultant magnetic field B is equal to B1 plus B2 plus B3 in vector form. Then resultant magnetic field is B1 mu naught I by 4 pi r minus j cap. B2 mu naught I by 4 pi r minus j cap plus B3 mu naught I by 4 r minus j cap. Then these two are same. Then resultant magnetic field is 2 into mu naught I by 4 pi r, means mu naught I by 2 pi r minus j cap plus this one mu naught I by 4 r into minus k cap. This is in vector form. And for magnitude, you know, resulting magnetic field is root of Vx square plus Vy square plus Vz square, means orthogonal vectors. Here j cap and k cap, minus j cap and k cap are perpendicular to each other. This is along y axis, and k capital Z axis. Here Px is 0, then resultant magnetic field magnitude is square root of mu naught I by 2 pi r square plus mu naught I by 4r square. This is magnitude of magnetic field and this is in vector form, and there can be so many questions on the basis of the combination of the concepts. So it may be asked, I am just showing you. Suppose it may be asked, this is a circle, this is center, this is center. Okay, this part may be given or may be removed. If it is removed, then current is I, this part is removed, this part is removed. Current I, current is flowing, current is flowing, current is emerging, this angle is theta. Then R2, due to this part, magnetic field is 0, this too, due to this part, magnetic field is 0, only you have to get this part and this part is 2 pi minus theta, convert to radian. Angle you got it, 2 pi minus theta, convert to radian, means theta by pi. Here 2 pi minus theta by pi. Okay. Sorry, 2 pi. Okay. Convert to the radian and put the value, you will get your answer. Okay. Then can I, or it may be given, Suppose current is I, it may be divided, this current I1, this current I2, again this current is I. Taking these two parts, this is a part, this is a part, take direction and accordingly add the magnetic field vectors. Okay. Okay, I am showing you another question. Some extent curl, but you can do it easily. Suppose I am showing you. This is center. This may be the question. Okay, this may be the question. I. Okay. This is a straight part. Current is I. We have to find magnetic field at O, radius is R. So this angle is theta. Again, this angle is 2 pi minus theta, convert it radian, then due to this curved part and due to this straight part. For straight part, you may divide this angle, theta by 2 and theta by 2. Then in accordance with addition of vector, you may add magnetic field to curved part and straight part and you can get your answer. There are so many questions. So you follow some good books, objectives, and your text also, NCERT. Then you can solve by yourself. They are fundamentals of this class. Then in next class, again we will meet with beautiful concepts. Thanks, my dear children. Thanks.